Today we're going to go through the 2019 AP Calc BC FRQs. I already have some other videos that go through the BC FRQs that are also AB FRQs, so that's number 1, number 3, and number 4. So in the next couple videos we'll go through the ones that are BC only, so number 2, number 5, and number 6. So starting off here with number 2, this is a calculator question, so you will need a graphing calculator to answer this question, and already by the looks of it I see that it's a polar area or a polar question. So let's get started. Number 2 here says, let S be the region bounded by the graph of the polar curve. R of theta is equal to this function of theta between 0 and square root of pi. Okay, it's nice of them to give us our bounds on our angle, as shown in the figure above. So part A is to just find the area of S. So here you'll want to remember that for polar area, we have that the area between the origin and a curve is given by 1/2 the integral from between the two angles that you're trying to go between, your r of theta all squared d theta. And this is really coming from the fact that when you are taking polar area, instead of kind of when you have a normal function, you're taking area by adding up little slices of area that are kind of vertical in nature. For polar area, your function is now defined by this radius, which is given as its distance from the origin. And so when you're finding the area under a polar curve, you're actually finding these areas of sectors of circles, or very tiny circles. This is a big one, but we're thinking about chopping this area up into really tiny pieces or sectors of circles, and the area of a sector of a circle is given exactly by 1/2 r squared times the angle that you're using. And here our d theta is representing that we're taking little tiny angles and we're adding up all the angles from alpha to beta. Okay, so that's just a little bit of intuition as to why this is the equation. But now to find the area of S, we just have to do that, plug everything in for what we have. So we know that our angles, it tells us that they go between 0 and square root pi, so we have 0 to square root pi, and they tell us our r also, so we're just doing this 3 square root theta sine of theta squared, and we want all of that squared d theta. Since this is a calculator question, you just plug this into your calculator, and you should get that this is approximately 3.534 when you round. And remember, on the AP test, you're always going to be rounding to 3 decimal places unless it tells you otherwise. All right, and so this is the area of S. Okay, part B says, what is the average distance from the origin to a point on the polar curve, r of theta? Okay, we're probably going to be using the equation for the average value of a function. Average value of a function on a closed interval. This is just really from Calc 1. Remember that that's given by 1 over b minus a times the integral from a to b of the function. If it said average rate of change, then that's going to be different. The average rate of change would be, just the slope between the endpoints. But it doesn't say that. We have average distance. And the hard part here is recognizing what they mean by what is representing this distance from the origin to a point. What we need to do here is find the average value of r of theta on the interval, so average value of r of theta on this interval from 0 to square root pi. So we have 1 over, that's square root pi minus 0, integral from 0 to square root pi of r of theta d theta. Okay, and again, we plug this into our calculator, and we get that this is approximately so you'll get that it's like 1.5799, but again, we want to round that to 3 decimal places, so we should get 1.580. This is our average distance from the origin to a point on that interval. Okay, part C here says there's a line through the origin with positive slope m that divides the region S into 2 regions with equal areas. Write, but don't solve, an equation involving one or more integrals whose solution gives the value of m. Okay, so this is a little bit trickier. Let's start by trying to picture what's going on. They're telling me that we have some line through the origin that splits this area of S into 2 equal halves. Splits this area in half. So in other words, you know, this area over here is equal to this area over here. And remember, what do they tell us about this slope? About this line, they tell us it has slope m. So in other words, the equation in rectangular coordinates of this line is y equals mx. Now the issue is that this is in rectangular coordinates, whereas our curve is in polar coordinates. So we really need to convert this statement into a statement about into an equation in polar coordinates. So to do that, remember that y is r sine theta and x is r cosine theta. So we're replacing our y and our x with those polar coordinates. And we're trying to figure out something about m, so we might as well solve for m. So this gives us m is r sine theta over r cosine theta. But that's the same thing, our r's cancel out, as saying m is tangent of theta. Which you could also see by recognizing that if this is our theta, we can draw a triangle, and what we know about the slope of this line is that it should be the rise over the run. And the rise here is going to be given by, again, our r sine theta, and our run will be given by our r cosine theta. So either way you want to see that, either going directly from rectangular coordinates to polar coordinates, or by looking at the picture and trying to think about, well, what do I know about the slope of this line? And remembering that slope is rise over run, and thinking about those in terms of this angle, but you're trying to relate this m to something involving r and theta. Okay, so what we have now is we know that m is given by tangent of our angle, and again, we're trying to figure out the m. We're trying to set up integrals that say that m, you know, this line of slope m divides this area into 2 equal pieces. Okay, so going back down here, there's two ways to set up these integrals. Okay, either you can say that the blue area needs to be 1/2 of the total area of S, or you could say that the blue area needs to equal the green area. And either of those should be answers that would be fine. But I think probably they prefer the first one, that the area of the blue is 1/2 of the total area. So again, we're just using our area equation, and so what I'm setting up here is saying the area of blue equals 1/2 the area of S. And again, I have that So the area of the blue should be given itself by 1/2 the integral from between its two angles. So we know we're going to start at 0. And then what angle should we go to? Well, we're trying to go to that line of slope m, right? We're trying to go to this line of slope m, and we know that the tangent of that angle is m. So that angle, then I could apply inverse tangent to both sides, and I get that this angle happens at the inverse tangent of m. So that's going to be my top angle here, inverse tangent m. And now remember, the equation is just 1/2 r squared. So this will be my r of theta. I'm not going to rewrite that all out, but that's this the normal equation for our r, d theta. So this represents the area of that blue section, and we want that to be 1/2 of the same equation we used for the area of S in part A. So this will be 1/2 of 1/2 the integral from 0 to square root pi of our r of theta squared. Okay, that's it. That's all you do. You just have to set it up. So really the hard part here was determining what this angle was, which we had to find by thinking about what m is in terms of polar coordinates, and then solving for that angle where that line happens, so we know where to stop taking our area. All right, finally, part D here says, for k bigger than 0, let A of k be the area of the portion of region S that is also inside the circle r equals k cosine theta. Find the limit as k goes to infinity of A of k. Okay, I definitely think this is the hardest question on this problem, which is appropriate since it's part D, right? One of the first places to start is to maybe figure out what these circles look like. Right off the bat, I honestly don't actually know where those circles are or what they look like. But luckily this is a calculator question, right? So on your calculator you could graph y equals cosine theta, or r equals cosine theta, r equals 10 cosine theta, r equals 50 cosine theta, something like this, just letting k get bigger. From here I did 1, 10, and 50, but you can choose whatever ones you want, just to get a sense for what these circles look like. And so if you do graph these, you'll notice that they're all circles that have, they go through the origin, and they get larger and larger going this way. They get bigger and bigger and bigger like this. And so we're trying to find the limit of this A of k as k grows larger. Where here, remember, we're letting A of k be the area of the portion of S that's inside this circle. And so what that area is going to be is it's exactly, as k gets big enough, these circles are going to encompass all of this area, all of the area from between 0, 0 and upwards to where this hits the y-axis. The circle will get big enough that it will kind of encompass all of this area. I'm not going to draw the whole big circle, but you can imagine that it'll get all of this area of S, and it just won't, it'll miss this little sliver, because these circles are always staying in the first two quadrants. And so all we need is then this limit of these A of k's is going to be given by the area from angle 0 to up, just the angle straight up, which is pi over 2. Okay, so what we get is that this equal to the integral 1/2, the integral from 0 to pi over 2 of our r of theta squared d theta. which again, you can plug that into your calculator. You'll see that this is about 3.324. It doesn't really ask for it, but if you wanted to, you could say, you know, because as k goes to infinity, you know, the portion, you could just say a of k contains the part of S in quadrant 1 and 2. Q1 and Q2. Okay. And that is it for problem 2 here. This was a tough FRQ. And notice how it really relied a lot on that equation for the area, polar area, that 1/2 the integral from alpha to beta of your radius squared. If we didn't know that, we would have not been able to solve very many parts of this problem. So definitely that is something to remember for the test. All right.
Don't forget to subscribe and hit that bell for all future notifications.